Before starting our discussion of hydrogen atom, it is important that we prepare ourselves a little bit. Keeping that in mind, today we are going to discuss a different coordinate system from the Cartesian coordinate, that is spherical polar coordinate, and also we are going to talk a little bit about this rather important quantity that we must have studied in physics, that is angular momentum. So, the question is, why is it that we need to talk about spherical polar coordinate? Why must we work in spherical polar coordinates if we want to build a quantum mechanical description in angular momentum? That is what we will learn in this lecture, and why at all talk about angular momentum, that will become clear when we start discussing our Schrodinger equation for hydrogen atom. So, spherical polar coordinates I hope are not completely new to most of us. The same point in space that we conventionally describe by coordinates x, y and z can also be described by r, theta and phi, where r is the distance from the origin 0, 0, 0 point. The angle theta is the angle between the z axis and the position vector, you can call, right. Position vector is a vector joining the origin to the point in question. So, the angle between z axis and that position vector is called theta, and then if we drop a perpendicular on the xy plane, let us say we drop a perpendicular on the xy plane, then the arrow, this blue arrow that we get, this is called the projection. Actually it makes sense for me to join the two tips of the arrow. If you drop a perpendicular from the tip of this arrow to the xy plane, then this arrow that we now get in the xy plane, that is the projection of the position vector that we are working with originally. The angle between the x axis and the projection vector, this is called phi. It is almost hidden by the globe unfortunately, so I will write again. This is called phi. Range of r is from 0 to infinity. Remember, r cannot go from minus infinity to plus infinity, 0 to infinity. Theta goes from 0 to pi, 180 degrees. You can ask, why is it that does not go to 360 degrees? Because it is not necessary. We are allowing one of the angles phi to go from 0 to 2 pi. So, the moment that happens, there is no need for us to talk about theta more than 180 degrees. That is why. So, of course, I mean one can think that theta should range from 0 to 2 pi and phi should range from 0 to pi, but this is the convention that is used everywhere. We should not build our own convention unless it is absolutely necessary. We go with whatever is the existing convention. So, remember, range of theta is from 0 to pi, range of phi is from 0 to 2 pi. Okay. The relationships are very simple, z equal to r cos theta, quite simple, right, because if you draw a perpendicular from this point to the z axis, something like this is perpendicular. What will be the length of the arrow on the z axis? That is a z component, right. So, that is z, and what is this angle? Theta. So, it is not very difficult to see that z is equal to r cos theta. Okay. R is missing here for some reason, but here it is written. R is the hypotenuse, z is the side, adjacent side. So, z is equal to r cos theta. What is x? Alright. So, this length is r. So, and this angle is theta, this angle is 90 degrees minus theta. So, I hope it is not very difficult to understand that the length of this arrow, the projection, that is r multiplied by sin theta. R multiplied by cos of 90 degree minus theta, that is r multiplied by sin theta. Now, Now when we look at this triangle here, you drop a perpendicular from the tip of the arrow on the xy plane to the x axis is a perpendicular. Now what we get is this here r sin theta, this is your hypotenuse and this is the adjacent side. So you get r sin theta cos phi. Similarly, y turns out to be r sin theta. R sin theta is same in both because r sin theta is the length of the projection here. So r sin theta sin phi, quite simple. You can work out the inverse relation. Here x, y, z, the Cartesian coordinates are subjects of formula. You can turn it around and make r theta and phi the subject of formula. I will not do that, you can do it yourself. What we get is r equal to square root of x square plus y square plus z square. That is of course very obvious, right. This is sort of the body diagonal r, and the lengths of the 3 sides of the cuboid are x, y and z. So of course x square plus y square plus z square is r square, or r equal to square root of x square plus y square plus z square. What is theta? Actually what is theta comes from the first relationship anyway, cos theta equal to z by r. So theta of course is cos inverse z by r. What is phi? The easiest relationship is that what is sin phi by cos phi? That will be y by x. So that is tan phi, is not it? So phi equal to tan inverse y by x. I said you do it, I won't, but then I ended up doing it because it is so simple anyway. Okay. So these are the relationships, and well, I think by and large we can remember it, but if required you can always derive it, it is not such a big deal. The point I want to make is that spherical polar coordinates are things that we are sort of introduced to very early in our lives when we are in school. If you think of a globe, we have all studied geography at some level and we know about latitude and longitude. What is latitude, what is longitude? Are they related to theta and phi? R of course is constant for the earth, that is the surface of the earth. But what about theta, what about phi? Theta is not exactly latitude, it is 90 degrees minus latitude, because latitude remember is defined from the equator. So what we call theta equal to 90 degrees in our system is written 0 degrees as far as latitude is concerned, and there the range is plus 90 to minus 90, right. So theta is related to latitude and phi is actually longitude, okay. Phi goes around like this, right, in the equatorial plane. So phi is exactly longitude, okay. Now we have been already introduced to this d tau business. We know that psi star d tau is the probability of finding the particle at some point r within a small volume element, and we had said that if you work in Cartesian coordinates x, y, z, then d tau is simply dx, dy, dz. When we work in spherical polar coordinates, it becomes a little different, and this is something that we will use, so we better learn. So here the diagram is drawn already, but I will still try to draw it so that we understand a little better. So let me draw here maybe. So suppose I want to define a volume element at this point. What do? I increase all the coordinates a little. So I can increase r by an amount dr. Of course the way I have drawn it, this is a large amount. Actually dr is very small compared to the length of r. Here I am exaggerating so that we see better, alright. Next what do I have to do? I have to work with theta. How do I work with theta? Change theta a little bit. So make it theta plus d theta. So now I can draw another line where this small angle here, well smaller than what it seems in this diagram, is d theta. So now see what will be the length of this r. Since d theta is a small angle, this length is going to be r d theta. So two sides of the volume element are defined already. One side is dr, the other side is r d theta. What about the third side? How do I define the third side? So drop this. Now I will increase phi a little bit like this. So now our projection will go somewhere here. Now I can think of this arc, this will be the third side of the volume element. Just draw a perpendicular like this arc is the volume element. What will be the length? Remember, this length here we already said is r sin theta, and I have increased the angle by d theta, d phi. So, this is going to be r sin theta d phi. I am not writing in a nice place. This is going to be, maybe I will write here, r sin theta d phi. So, the three sides of the volume element are defined now. Just to see whether we understand it or not, I will draw the other sides of the arc as well. Let us hope I have not forgotten which color I used. Okay, this is one, and now I will draw R. This is R, again you have to increase this as well, and just because I am a little bored of changing colors, I will complete the volume element with the same color anyway. So, I hope you see the volume element here. The volume element is not exactly a cuboid, it has curved sides, but the curved sides are almost linear because they are small segments of a large sphere, you can think. And in case you have had trouble understanding my poorly drawn diagram, here you have a little better diagram. Here also you see the sides are dr, r d theta and r sin theta d phi, right. So, the volume element, volume of the volume element is going to be r squared dr sin theta d theta d phi. This is very important and we are going to use this later on in our discussion. Now, let us talk about angular momentum. As you will see, when we discuss hydrogen atom, angular momentum is going to be a very important property that we will worry about. I think once again we all know that angular momentum is defined as the cross product of r and p, r cross p. What is the meaning of cross product? R is a vector, p is a vector, L is also a vector. So, L is the vector product of r and p. What is the magnitude of L then? Magnitude of L is going to be rp sin theta. And what will be the direction? Direction will be perpendicular if this to the plane of r and p. R and p will always be in some plane. So, direction of L is going to be perpendicular to that. Okay. Now, let us work out what this is, and while doing that it makes sense if you work with x, y and z components to begin our discussion. So, we will write r like this, I, j, k are the unit vectors along x, y and z respectively, and x, y and z are the scalar values of x, y and z respectively. So, r vector is given by I vector multiplied by x plus j vector multiplied by y plus k vector multiplied by z, and p vector is given by I vector multiplied by px plus j vector multiplied by py plus k vector multiplied by pz. We want to work out what is L equal to r cross p, and when we do that, this is what we get. Okay. First of all, why do we have 6 terms and not 9 terms? We should have got something like I cross I x square also, right. Well, the thing is we need to remember this, I cross I, j cross j, k cross k, everything is equal to 0, alright, because remember what the magnitude is going to be, it is going to be sin theta, right. I square sin theta, that kind of thing would have happened. The angle between I and I, j and j and k, this angle is 0, sin theta is 0. Okay. So, cross product of the same vector with itself is 0, we do not have to worry about that. What about the others? I cross j is equal to k, right. Remember these are all perpendicular to each other. So, k is perpendicular to the, so k is basically along z axis, it is perpendicular to the xy plane, and j cross I is minus k, that is important to understand. Okay. So, if you change the order in this vector product, the direction is going to change even though magnitude will remain the same. So, and it is very easy to remember also, I cross j equal to k, j cross k equal to I, k cross I equal to j in alphabetical order. Go in alphabetical order. If you are going in alphabetical order, you are going to get positive, and if you go in anti alphabetical order, j cross I, that will be minus k cross j minus I cross k is minus j. It is as simple as that. If you just want to remember it, of course you can work it out and see what it is. So, let us see in this expansion that we have performed, let us collect the terms in I. Remember, I is obtained by taking cross product of j and k, that is I, and cross product of k and j is minus I. So, j and k, j cross k ypz, this becomes I ypz, and we have k cross j zpy, that becomes minus I multiplied by zpy. So, if I collect the terms in I get I multiplied by ypz minus zpy, this very nice symmetric expression, and the other two terms also turn out to be like this, plus j multiplied by zpx minus xpz plus k multiplied by xpy minus ypz. So, see what is ypz minus zpy? That is the x component of the angular momentum, right, because it is multiplying the unit vector along x direction. What is zpx minus xpz? It is the y component of angular momentum, and what is xpy minus ypx? That is the z component of angular momentum. This is conveniently written in the form of a determinant I multiplied by ypz minus zpy minus j multiplied by xpz minus zpx, which boils down to plus j multiplied by zpx minus xpz plus k multiplied by xpy minus ypx. Okay. It is a very simple determinantal form in which we can write this. So, this is the classical description. Now, let us think how we are going to write the same expressions in the language of quantum mechanics. Remember, in quantum mechanics we have an operator for every physical observable. Operator for x, y and z are just position multiplying the wave function. Operator for something like px would be h cross by I del del x. Operator for py would be h cross I del del y. For pz the operator is h cross by I del del z. So, all we have to do is in this determinant we have to substitute x, y and z by x hat, y hat, z hat respectively, and we have to substitute px hat by h cross by I del del x and so on and so forth. When we do that, this is the angular momentum operator that we generate. If you know position and momentum operator, you can virtually generate all operators that you require. So, L hat operator is given by h cross by I multiplying this determinant ijk x y z del del x del del y del del z. This is what it is. Now, we will have something to say about the total angular momentum and z component of angular momentum starting from here. Basically, we want to write down the operators for total angular momentum and z component of angular momentum in terms of spherical polar coordinates. You will see why the problem actually becomes simple. And why are you worrying only about z component? We will say that as well, even though it might be taking things a little too far for this particular course. So, in case you find that discussion to be too much, you can just skip that part. It depends on whatever is being done in your college. Alright. So, Lx hat, as we said earlier, is ypz minus zpy, Ly hat will be zpx hat minus xpz, Lz hat will be xpy hat minus ypx hat. So, and then when we write the expressions for the p q hat kind of operators where q can be x or y or z, this is the expression that we get. Now, you know the relationship between r theta phi and x y z. Using these relationships, it is possible to convert from this del del z del del y to things like del del r del del phi del del theta. It is a little longish, so we are not going to do it here. If you are interested, it is not difficult, it is just a little too long, you can do it yourself. So, it turns out that in spherical polar coordinates, Lx hat operator is minus IH cross multiplied by minus sin phi del del theta multiplying minus cot theta cos phi del del phi. You could also write H cross by I here instead of writing minus IH cross. For Ly hat, the operator looks very similar. The only difference is wherever you have sin phi for Lx, you have cos phi for Ly. Lz hat is the best of them all, minus IH cross or H cross by I, you can write minus IH cross or plus H cross by I multiplied by del del phi. Very convenient, that is what we are going to work with. And the other operator that is very important is not L, we generally do not work with L, we work with square of angular momentum, and that operator is obtained by taking Lx square plus Ly square plus Lz square. And to cut a long story short, this is the form of the operator. This is something that will keep on coming back in our discussion later on. Do you have to remember this? For God's sake, no. We should provide this whenever it is required. There is no need to remember too much here. If you remember del del phi multiplied by H cross by I am very happy. L square please do not try to remember, it will be provided in our discussions wherever required. Okay. So, these are the two operators that we are going to work with, Lz hat and L square hat. Now, why is it that we are not interested in Lx and Ly? Because again we are not going to do the derivation. If you are interested in the derivation, I recommend that you see my lectures that are available on YouTube for a more elaborate quantum chemistry course. You have to write Anindya Datta quantum and search within YouTube, you will see 68 lectures and they are named. So, you go and see, go through the angular momentum lectures, you will get answers to whatever questions you might have at this point. For now, let us take it axiomatically that in quantum mechanics, if two operators commute, what is the meaning of commute? Meaning you take a wave function, make A hat operate on it first and then make B hat operate on it, you get something. Then you reverse the sequence of operation, make B hat operate on it first and then make A hat operate on it, you get the same answer. So, another way of writing it would be this. What I am saying is you have some wave function phi, I will just write phi here, make A hat operate on it, you get something, let us say A multiplied by phi. Now make B hat operate on it. Okay. So, basically B hat is operating on A hat phi. Okay. So, this is what you get, B hat operating on A phi. The other sequence, let B hat operate on phi, you get let us say B multiplied by phi. Now let A hat operate on this B hat phi, this is a phi, sorry. Then you get A hat operating on B phi. It can be proved, we are not going to prove here, that B hat A hat phi is equal to A hat B hat phi, or you can write like this, A hat B hat minus B hat A hat phi equal to 0, that in the convenient notation that we write like this. A hat comma B hat within third bracket means a commutator, A hat B hat minus B hat A hat. B hat A hat, what is B hat A hat? B hat comma A hat, the sequence of operation is just opposite. Of course, in this case it will be same, but the crux of the matter is that if the commutator is 0, then they have a common set of wave functions and properties associated with A hat and B hat can be determined simultaneously. It turns out again we are not going to prove it here, it is there in those angular momentum lectures. It can be shown that L square hat and Lz hat commute. That means you can determine the square of total angular momentum and the z component of angular momentum simultaneously for a system. However, Lx and L hat, Ly and Lx hat and Ly hat, Ly hat and Lz hat, Lz hat and Lx hat do not commute, they do not commute. So, Lx and Ly, Ly and Lz, Lz and Lx, they cannot be determined together. Okay. So, the only hope you have is to determine the total angular momentum and its component along one direction that we call z direction. Here students usually have this question, what is z direction? I am talking about hydrogen atom, let us say. How does the atom know what is z? Atom does not know. Remember wave function collapse. Remember that everything is when your system is in an entangled state before you make the measurement, only when you make the measurement the wave function collapses into something. Suppose I want to measure the z component of angular momentum. How do I see it experimentally? I apply a magnetic field, is not it, Zeeman effect. So, the direction of the magnetic field becomes the z direction. What we are saying is, if we have an angular momentum, we have an angular momentum like this. Okay. When we apply a magnetic field, right, now this z direction is defined. So, theta is defined with respect to the direction of the magnetic field. Now, we can determine the length of this arrow, which is the angular momentum itself. Actually, we can determine square of it. We cannot really determine whether it is pointing up or down, just from here. L square is what we can determine. And the other thing that we can determine is the z component. Okay. So, from here you get L square, from here you get Lz. Combining the two, you can say whether the arrow is pointing up or down, of course. This is what we are going to discuss in a little more detail when we talk about hydrogen atom.